We are now going to move out of the world of logic and reasoning and sets, and we're going to start talking about number systems. And we have a quote here. It took men about 5,000 years counting from the beginning of number symbols to think of a symbol for nothing, by Isaac Asimov. And what he's referring to is the fact that it wasn't until the 15th century until 0 was added to the number line and accepted as a number. We didn't think we needed a number for nothing until very, very recently in mathematical history. So we need some background information if we're going to attack our next topic in a strong way. And that background information is exponents. So an exponent, b to the n, is equal to b times b times b n times. I'll change to a brighter color. So we have an exponential expression, which is 8 to the 1. It is read 8 to the first power, and it's evaluated as 8 to the 1 is equal to 8. 5 to the 2, or 5 squared, or 5 to the second power, is 5 times 5, which is 25. 6 to the third power, if you're multiplying 6 3 times, you say cubed, or 6 to the third power, or 6 times 6 times 6 is 216. And then something like 10 to the fourth power is just called 10 to the fourth, to the fifth, to the sixth, onward after that. And 10 times 10 times 10 times 10 is just 10 with 4 zeros, or is a 1 with 4 zeros after it. And that's exponents, basic exponents. So we live in the world of the Hindu-Arabic number system. We are base 10, where we have 10 digits, 0 to 9. But why is that important? What's important about that? We only have a base 10 number system because of reasons like us having 10 fingers. It's easy to count. If you have 10 fingers, it's easy to count in a 10-digit number system. And because of that, because of our 10-digit number system, our base 10 number system, we can express numbers in the following way. 663 is equal to 6 times 10 squared, plus 6 times 10 to the first, plus 3 times 10 to the 0. That's why our number system is a positional value or a place value system, because the position of each digit can be described with the power of 10 that it's associated with. For example, the number 3,407 is equal to 3 times 10 to the third power, plus 4 times 10 to the second power, plus 0 times 10 to the first power, plus 7 times 10 to the 0th power in our positional number system. And the same with this one here. We have 0, 1, 2, 3, 4. So we would have 5 times 10 to the 5th plus, 0, 1, 2, 3, 4. So we would have 5 times 10 to the 4th plus 3 times 10 to the 3rd plus 5 times 10 squared plus 2 times 10 to the first power plus 5 times 10 to the 0. And then we can go in the other direction. These numbers right here, this is just 754. And then the next one is just 6 in the 5th place. And then we have 0, 0, 0, all the way down until we have an 8 in the tens place and a 0 in the ones place. Let's make sure I did this right. 0, 1, 2, 3, 4, 5. Yeah, exactly. So this would be 600,080. Now, why are we talking about this? What makes the number 10 so special? What if we had 2 fingers? Back when computers were first being made, we needed to develop a simple way to talk to them and tell them what we wanted to do. And so we worked in a number system called binary, which is a number system where everyone in the world would have 2 fingers. And binary works like this. If I have 0, then I have 0, just like always. 0 is equal to 0. But if I have 1, I still have 1. But then if I want to have 2, just like how when we want to have 10, we restart. 1, 0 is equal to 2. Because This is the 2 to the 0th place, and this is 2 to the 1st place. So we have 1, 2, and 0, 1s. And that is the binary number system, and we'll do a little bit more with the binary number system, and we'll do explicit problems. But it was mainly started to become popular when we wanted to talk to computers. When we were first learning to talk to computers, we would have these little punch cards, and we would punch a hole if we wanted it to be a 1, and if we didn't want it to be a 1, if we wanted a 0, there would be no punch, and then you would just feed the cards into the machines, and that's how you would tell them what you wanted. That's how you would say numbers and letters and anything else. Computers still talk in binary, but now we have more advanced computers. They talk in other number systems too. So, the binary number system. There are 1-0 types of people in this world, those who understand binary and those who don't. The joke there is that 1-0 in binary is 2. So let's make a table with base 10 on the left and base 2 on the right, just for a few numbers, and see what happens. So if I want the number, this is base 10, this is base 2, and let's just go until we run out of space. If I want the number 1, in fact, if I want the number 0, it's equal to 0, 1 is equal to 1. But if I need a 2, I move over and I get a 1, 0. Then if I want 3, I have 1, 1, which is 1, 2, and 1, 1, which is 3. Now if I want a 4, I add another 1, and everything restarts. I end up with a 1, 0, 0. That's 1, 4, 0, 2s, and 0, 1s. And so on and so forth, and the binary number system keeps going like that. So in the next video, we'll talk a little bit about converting from binary back to base 10 and base 10 to binary, and maybe even some other number systems.